SwayamPrabha. Digital India. Educated India.
Hello and welcome to lecture 18, module 3 for design concepts. So in last lecture we were discussing about very important aspect for say design of axial flow compressor, or say maybe we can consider for design of any turbo machinery. We have come up with the equation, that's what is called radial equilibrium equation. So that radial equilibrium equation, that's what will be helping us in order to determine the variation of my pressure along my span. So that's what is a function of my tangential velocity component. So we can say my dP by dr, that's what is rho Cw square by r. Then based on our fundamental understanding of thermodynamics, we have come up with the formulation, that's what it says, my stagnation enthalpy change along my radius, that's what is a function of my axial velocity and change in axial velocity, component of tangential velocity and tangential velocity variation along with my centripetal force. Now if we recall, we have done certain assumption. We assume the work done to be constant along the span. We have assumed our h to be constant along my span, that is, it is not varying from hub to tip. Second assumption what we have made, it is we are assuming our axial velocity to be constant. So that's what is not varying along the span. And based on these two assumptions and using this formula, we come up with the formulation, that's what is we have defined as a free vortex flow. So you can say, it says the variation of my whirl component, that's what is following the rule, it's a free vortex rule. Now you can understand based on our assumption what we have come up with, that's what is very useful for our further movement. So what it says, if we are considering arbitrary variation of two of the variable, suppose say my work done and my axial velocity, suppose if I consider my axial velocity and tangential velocity component, based on those assumptions, it will be possible for us to calculate the variation of our third component. So that's what is the use of our vortex energy equation. So now we will be discussing in detail how do we move forward with our detailed understanding for further design aspects. So before going into detail, say we have simplified our problem, we have derived with our radial equilibrium where we have not considering any variation of radial velocity component. Now Smith in 66, he has given full radial equilibrium equation, and according to him this is what is been represented in sense of my say 1 upon rho equal to dP by dr, that's what is 1 upon r Cw square minus 1 upon Rm Cm square cos phi minus Cr dCm by dm. Now let's try to understand what exactly is the meaning here. So here if we look at, we have discussed because of my flow passage, because of change of my area, we will be having radial velocity, that's what is coming into the picture. And in order to simplify that case, what they have done, say having say this is what is my axial velocity component, you can understand the magnitude, and here we are having radial velocity component. So rather considering my axial flow as a velocity component for my fluid to move, they have considered this meridional velocity component. So here this is what is phi, that's what is representing what will be the inclination of my flow, and how my area change, that's what is affecting the movement of my streamlines. So here if you look at this Cm, as I told, it is a velocity in meridional direction. dCm by dm, that is nothing but it's acceleration in meridional direction, and this term 1 upon Rm Cm square cos phi, it is radial component of my centrifugal force in radial direction. So if you are putting all together, that's what is giving us idea about how my flow three-dimensionality that will be coming into the picture, and how do we use our radial equilibrium theory. Now, in order to simplify the problem, we are not considering this variation, but the present trend, say when we are designing our single stage, this variation it is not making much sense. But when we are analyzing all stages, suppose say HP compressor, it is made up of 10 stages. So under that condition, this calculation, that's what is must. Suppose say my LP compressor, it is made up of number of stages, there this calculation, that's what is must. So people, those who are working for the development of CFD codes, they are considering this analysis for flow field analysis. Okay, here in this case they are considering how my change of radial velocity, that's what will be coming into the picture. So more trained, mostly for all engine manufacturing companies, they are having their own code for say simulation. So in line to that, many people in university level, they are also working on analyzing this flow. This is what is called streamline curvature method. We will not be discussing this into detail, but this is what will be giving us idea what is our full radial equilibrium equation. Now here what we have analyzed, say we have come up with our equation, it says Cw into R equal to constant, and we have defined that as a free vortex design. So what all assumptions we have made, we have assumed our work done to be constant along my span. We have considered, say there is no variation of my stagnation enthalpy. Then we have assumed our axial velocity, that's what is not going to change along my span. And based on this two, we have come up with the formulation for free vortex. That's what it says my vortex, or say my whirl component, that's what is varying in a systematic way. That's what is called Cw into R equal to constant. So you can understand, if I consider my variables as say H0, Ca, Cw, if they are not varying or remains constant in radial direction, then we can say then and then only my radial equilibrium is getting satisfied. So basically, in order to satisfy the radial equilibrium, these three conditions must satisfied. That's what is the need. Okay. Now along with this, we are more interested in our parameter. That parameter we are defining as a degree of reaction. Now the situation is, question always will come, what is happening with our degree of reaction if we are making this assumption. Okay, so we can say my degree of reaction, that's what is given in sense of alpha and in sense of my beta. If I'll be simplifying my equation, it says my degree of reaction will be coming as a 1 minus constant by R square. Now if we try to understand what is the meaning of this equation, you can say my degree of reaction, that's what is varying with my radius. So you can say it will be increased progressively from root to tip. We can understand root is nothing but that's what is my hub, and tip we can say that's what is my casing. So you can say you will be having great variation of degree of reaction all the way from hub to shroud. Now we can say if the stage has desirable value of 50% reaction, it may possible that near my hub, my degree of reaction, that's what will be going to be reduced. Okay, because we can understand my degree of reaction, it is a function of my radius. It may be possible because of that my angle that will be coming to be large. That's what will be giving highly twisted blade. So you can see here, say this is what is my case. If you look at near the hub region, my delta beta, that's what is coming to be large. And here near my tip region, my delta beta, that's what is coming to be slightly lower. But we need to understand why this delta beta, that's what is coming to be higher. We must realize our peripheral speed, that's what is a function of my radius. Okay, so you can say if I am considering my peripheral speed to be lower near the hub region, then I need to have great deflection of my flow near the hub region. Okay, and that's what is in order to achieve high pressure rise or in order to do more work in that particular region. Okay, so that's what is asking for more amount of diffusion in that region. It may be possible that you will be calculating your degree of reaction, and that degree of reaction that may be coming to be lower. Sometimes when you are doing your calculation, you will realize when we will be doing the actual design, you will find degree of reaction is coming negative. Now we know when I say degree of reaction to be 0, that means whole my diffusion, that's what is happening only in my rotor. Is it? Okay. Now the situation is, this is what is wrong. We say my degree of reaction, that's what is coming to be 0, my whole diffusion, that's what is happening in my stator. Okay. Now if I say my degree of reaction, that's what is coming to be negative, that means in place of having diffusion to happen, there I will be having the acceleration of flow. So that particular region, rather acting like a diffuser, it will be acting like a nozzle, and that's what will lead to losses. So that particular region, that will not be giving me pressure rise. So that's what is coming in sense of loss. Okay, so we can say I should avoid my degree of reaction to go 0 or maybe in a negative value. This problem, that's what will get aggravated when you are having your hub to tip radius ratio, that's what is say reduced. So we can understand when we are having our hub radius, that's what is coming to be lower, it is but obvious my peripheral speed is going to be lower. We will discuss this point again, but at this moment just try to understand our degree of reaction, that's what is varying from lower value at the hub and having higher value near the tip, and that's what is giving highly twisted blade. When I say highly twisted blade, that's what is a problem with our design. When I say design problem, when we are giving those kind of blade for manufacturing, because of highly twisted blade, it will be more challenging to fabricate those blades. Okay, it is not that people, they are not making or not doing design based on free vortex. Yes, as on today also people, they are preferred to go with the design of free vortex, but as I told, we need to be very careful in sense of setting our degree of reaction near the hub region. Okay, now say what we have discussed, that's what it says my free vortex formulation. So let me rewrite the equation. Say it is more generalized vortex flow, we can write down Cw into r to the power n equal to constant. What I am doing, I am just replacing r by r to the power n. In that, if I will be putting my n equal to 1, that's what is giving what we say as a free vortex design. Okay. Now normally this n, that's what is varying between -1 to 2. Okay. Now let's try to understand what is the meaning of these numbers. So here if you look at, when we are having our n, that's what is in between 0.75 to 1, we can say this is what is defined as a relaxed free vortex design. Okay, and that's what will be giving the overloading of my blade with respect to free vortex design. We will see where exactly we are looking for such kind of configuration. So you can say, when I am changing my r to the power n, if I'll be putting my n, that's what is creating, say, different kind of design aspects. Okay. Now if we are considering, say, my n, that's what is greater than 1, that's what is giving me underloaded design with respect to free vortex design. Okay, and if I'll be taking my n equal to -1, that's what is often, that's what is defined as a force vortex design. Now we need to realize, we are having limitation with our free vortex design. We have two limitations what we have discussed. One, that's what is having highly twisted blade, and second, that's what is with the change of my degree of reaction. Okay, so that's what is putting constraint to designer to design the blade, and in order to get rid of those limitations, people, they have come up with, say, having, say, different approach, and this is what is the approach what we are writing at this moment. Okay, that's what is Cw into r to the power n equal to constant. Okay. Now suppose if we are considering this is what is my variation of whirl component, we must realize this is nothing but that's what is representing how my whirl component or tangential velocity component, it is varying along with my radius. Okay, do not misinterpret in other way. Just try to understand here, say my Cw into r to the power n at particular station, that's what is constant. Okay, suppose say this is what is my blade at mid station. If I know what is my Cw, if I know what is my Rm, I can calculate that constant. Now based on that, if I am considering if my design, that's what is say free vortex design, I can calculate how my Cw, that's what is varying along my span, because I will be changing my value of r. So we will see what exactly and how exactly we will be doing the calculation for our free vortex part. Okay. Now it says for most modern designs, the tip section and hub section, they are deliberately offloaded by using n equal to 2. That's what we were discussing earlier. The reason is, this is what is in order to minimize the tip and the losses, that's what is related to end wall. So near the hub region and near this tip region, we will be having the variation of n, that's what is n equal to 2. Okay. Now at the mid section, they are overloaded. That means in order to compensate for what losses in loading we are getting, just understand when I am taking n equal to 2, that means it is not that much loaded. Okay, in order to compensate that loading or in order to achieve that loading, we are considering this n equal to 0.8 near the mid stations. Okay. Now this is what is giving us the flexibility in sense of selection of our design approach. Okay, and we are able to lower the losses, and that's what will lead to increase in efficiency or the improvement in the efficiency of that particular stage. Now there are other special requirements. So as we were discussing, we are not having only approach to improve the efficiency. We have other criteria, say we are looking for, say, improvement in overall operating range. We are looking for improvement in off design condition. We are looking for the stability of my flow, or we can say we would like to enhance the operation of particular stage for compressor. Okay, and for that case, for most of the organization, they are having their own design database, and based on their understanding, based on their experience, based on their computational work, based on their experimental work, they have made their database, and again when they are doing the design, that time they are using that approach. Let me tell you, do not underestimate the design of, say, your axial flow compressor. It is not that we will be taking one compressor, one axial flow compressor stage from one engine to other engine, and that will work. All these axial flow compressors need to be designed indigenously. So all engines, they are having their compressor design. That's what is indigenous design. Let it be LP compressor, let it be HP compressor. Okay, so you can understand that's what is running the whole industry for, say, gas turbines. Okay, and when we are talking about the special application for aero engines, that will be more challenging. Okay, now let's move. Suppose if we are considering, say, high bypass ratio design. Say this is what is, say, my high bypass ratio fan. Now you can understand some amount of air that will be entering inside my LP stage here. So you can say this is what is called inner stream, and outside, that's what is called outer stream of my bypass ratio fan, or say bypass fan. Okay, it says if we are considering, then the law what we are talking about the design, that's what is, say, my design using, say, energy equation, vortex energy equation, that's what is not straightway applicable here with certain assumptions. What it says, my inner stream, that's what is giving the high, that's what is moving towards, say, high pressure core. So this is what is called core engine. Okay, and that's where the pressure ratio requirement, that's what is to be lower. So here what air, that's what is entering inside this core, that's what is entering at the low pressure. When we are considering on the upper stream, we are, if you look at, that's what is having, say, high pressure ratio. So you can understand when I say my fan, it is having the pressure ratio of 1.6, 1.8, 2. That's what is been distributed along my span. Okay, so that's the reason why the design of these fans, they are always challenging. Okay, not because of size, but you can understand the operation requirements are different. So under that condition, we need to consider, say, we can say my dH0 by dr, that will not remain 0. So you need to literally sit down and calculate dH0 by dr based on change of my axial velocity, based on change of my tangential velocity component, and based on my centripetal action. Okay, so this is what is giving you some of the idea in sense how do we approach with the design. But still, let's try to move in part. We can say we have discussed when we are having our Cw into r to the power n equal to constant, we have discussed different approaches. But as on today, for our compressor design, people, they are taking different design approaches. One of them, as we have discussed, is a free vortex design in which r into Cw, that's what is equal to constant. Okay, if we say my Cw divided by r, that's what is equal to constant, that is defined as a force vortex concept. We can have constant reaction design, so where we are considering our degree of reaction to be constant. There are approaches people, they have come up with, that's what is called exponential design approach, where my whirl component after the stator and at the inlet of my rotor, that is given by Cw1 equal to A minus B by R, and at the exit of my rotor we can say Cw2, it is given by A plus B by R. Now you can understand how people, they are thinking of changing this formulation. Now they have come up with a different kind of approach for designing. We will be discussing this part. So it says the free vortex design, people they are saying that's what is giving the highly twisted blade, and that's the reason why it is not advisable when my blade height is small. Okay, because that's what is giving highly three-dimensionality of my flow. And it says current design practice for transonic compressor, people they are taking the approach of constant pressure ratio across the span. We have discussed. Say when we are talking about the design of fan, that's where we are considering some other kind of approach. Okay, so the normal design pressure process, that's what will be having two different kind of possibilities. One possibility we can say it is constant specific work input at all radius, and second that's what is say arbitrarily world velocity distribution. Okay, let's have look at what exactly is the meaning here. Now what we have realized, let's say if we consider I am having constant work done or constant work input at all the radiuses, and if we consider my whirl component, that's what is varying with the radius, and that's what is given by arbitrary whirl velocity distribution. Okay, this arbitrary whirl velocity distribution we are writing as say after stator or at the entry of my rotor. Just do not get confused. The meaning of after stator means, suppose say I will be having first stage, at the exit of my stator that will be the entry of my rotor for the next stage. That's what is given by A into r to the power n minus b by r, and my Cw2 we can write down A into r to the power n plus b by r. That's what is at the outlet of my rotor, because we are more interested what is happening with the change of my tangential velocity. Remember one thing, the change of tangential velocity, that's what we are correlating with our work done, and we are correlating that with my pressurizing capacity. So again and again when we are talking about tangential velocity component, do not get confused what is the use of tangential velocity component, because this is what is a main parameter what we need to understand. If we consider say my H01 and H02, that's what is constant, say what we have assumed as a constant specific work input. If I'll be putting that, so my W, that's what will be changing in the form of 2b into omega. You can say that's what is independent of my radius. Okay, and that's what is we are assuming. What is our assumption? We say my constant specific work at all radiuses, and second assumption what we are discussing is a arbitrary whirl velocity component, and these two equation, that's what seems to be compatible in sense of moving further. Okay, so if we consider here, say this is what is say arbitrary whirl velocity distribution what we have, and we can say at the entry of my rotor I will be having my Cw1, and at the exit of my rotor I will be having my Cw2. Now we have correlated this Cw1 and Cw2 in the form of exponent n. So if we are writing in this equation, if I'll be taking again say my n equal to 0, that's what is giving me my exponential design. Okay, if I'll be taking my n equal to 1, that's what is giving me constant reaction design, and if I'll be taking my a equal to 0, that's what is saying my free vortex design concept. And suppose if I consider I am having my b equal to 0 and n equal to 1, that's what is giving me force vortex design or say first power design. So we are more interested in considering arbitrary variation of whirl component, because we have realized we will be simplifying our calculation by assuming the free vortex concept, but still we need to go with other approaches too in order to understand what is happening. Now the question may arise in our mind, what about these constants a and b? So here if you look at this CW, as we have discussed, at the entry CW1 and at the exit my CW2. What we know from our fundamentals, this A and B, that can be calculated based on our degree of reaction and what we can say my stage temperature rise. Okay, so here if you look at, this is what is representing my degree of reaction. That's what is 1 minus CW1 plus CW2 by 2U, and this work, that's what we are representing, U into CW2 minus CW1, and that's what we have derived here. If you are simplifying this equation, you will be getting your A, constant A. That's what is in the form of my peripheral speed at the midsection, my degree of reaction at the midsection, and this is what is varying with my radius. Okay. Same way my B we can calculate based on my stage temperature rise, and that is what is a function of my R. So you can understand this constant A and B, they are also function of my radius. Okay. So we can calculate what is our value of A and B at the midsection, such that it will be easy for us in order to understand or in order to calculate our arbitrary wall velocity distribution at the entry as well as exit. Now what all we were discussing about, that's what is say my exponent n equal to 0, my n equal to 1, my constant A equal to 0, constant B equal to 0 and n equal to 1 configuration. That's what will be giving us some idea for say future designs. So in next lecture we will be discussing about how do we use this concept for further design of axial flow compressor. Thank you very much for your attention.